Hello everyone, I'm Christina and welcome to the next video in our A-level trigonometry series. This is part 2 of solving trigonometric equations. So our objectives for this video are just to continue solving trig equations, this time within a different given interval. We also want to solve one where the solutions are not restricted to a particular interval. So we're going to give a general solution for this. And then we also want to see how we solve trig equations involving a few compound angles. So let's have a look at that in our first example here. So we want to solve 6 cos squared 2 theta equals 5 plus sine 2 theta. So what will first be useful is to recall that cos squared theta plus sine squared theta equals 1. And this also applies to our double angles. So cos squared 2 theta plus sine squared 2 theta also equals 1. Now, if we rearrange to make cos squared 2 theta the subject, we can write that as cos squared 2 theta equals 1 minus sine squared 2 theta. So I'm moving that sine squared 2 theta onto the left-hand side. And now what I can do is I can substitute in this rearranged expression for cos squared 2 theta into my original equation. So substituting into 1. And so what will that give? On the left-hand side, I'll have 6 lots of 1 minus sine squared 2 theta equal to 5 plus sine 2 theta. And so I'll multiply that out. So I get 6 minus 6 sine squared 2 theta equals 5 plus sine 2 theta. Now what I want to do is get all the terms on one side and equate this to 0. And we're going to see if we can recognize the structure. You might be able to see it already, but let's move all the terms onto the left first. So I'm going to minus both sides by 5 and minus both sides by sine 2 theta. And so on the left, I'm left with 6 sine squared 2 theta minus sine 2 theta. And then we have 6 minus 5, that's plus 1 equals 0. To clean this up a bit, I would like a positive coefficient in front of that sine squared 2 theta. That's going to make things a bit easier. So I'm going to multiply every term by minus 1. You don't have to do this step. You could instead move all of those terms onto the right-hand side and then just equate that to 0 as well. So 6 sine squared 2 theta plus sine 2 theta minus 1 equals 0. And so if you can't already see it, this is in the form of a quadratic equation. And you might be able to see that better if I write sine 2 theta equal to some variable u. And so if I put that back into this quadratic here, I'll get 6u squared plus u minus 1 equals 0. Because u is sine 2 theta. So that's how I get to that step. So now we have a quadratic which we can solve. You can either use the quadratic formula or you can factorize here. I'm going to factorize. So 3u in the first bracket, 2u in the second. So now we have to think about the numbers that go here and here. Well, if I put positive 1 there, and I put negative 1 there, I know negative 1 multiplied by 1 give me negative 1. And if you multiply it out, you should see that you will get the rest of it there. So you'll get u and 6u squared. So you can just have a check of that for yourself. So now I can write the solutions to this. I can write u equals 1/3 because the brackets have to be 0. So either 3u minus 1 is 0 or 2u plus 1 is 0. So u is 1/3 or u equals -1/2. But remember that u is sine 2 theta here. So in fact, sine 2 theta equals 1/3 or sine 2 theta equals -1/2. Okay. If we have a look at our graph of sine theta down here, we can use it to find the solutions. Okay, so notice that this is, our solutions are sine 2 theta, but I've drawn a sine theta graph. Now, changing the coefficient in front of theta will change the shape of our graph, but we're going to look at that in another video where we're looking at transforming trig functions. So for now, let's focus on getting the actual solutions themselves. So for sine 2 theta equals 1/3, well, let's think about where 1/3 will be here. If we have 1 here, that's our maximum value for sine, and we have -1 here, 1/3 is going to be about there. Doesn't have to be perfect, we're approximating. That's our first solution, and then we have -1/2. So -1/2, let's put it there. Okay, around there. So 1/3. So what we can say is that for sine 2 theta equals 1/3, we're kind of solving it as if we're solving just for sine theta initially. So what are our two values here and here? And that comes from the symmetry of the graph. So this initial value will be 2 theta equals sine to the -1 of 1/3. And then our second solution, which comes from the symmetry of our graph, is just going to be pi minus sine to the -1 of 1/3. So those are our initial values that we're going to use. And I will write that on the right-hand side. So I can write 2 theta equals sine -1 of 1/3 and pi minus sine to the -1 of 1/3. And then let's have a look at sine 2 theta equals -1/2. Well, we have a value here from our graph that we can see as a solution. And that's actually going to be minus, that's going to give us 2 sine theta is sine to the -1 of -1/2. Again, using our exact trig values, we're going to get minus pi over 6. So 2 theta is minus pi over 6. And again, we have another solution here from the symmetry of the graph. That's 2 theta equals pi plus pi over 6. Okay, so that's 7 pi over 6. And so I'll write that there as well. So 2 theta is also equal to minus pi over 6 and pi plus pi over 6. Let me just write that as 7 pi over 6. But remember, we have just worked out our solutions for 2 theta using our sine theta graph. So all we really need to do now is to divide by 2. So our final solutions will actually be theta equals sine to the -1/3 over 2. So I'll stick a factor of a half there. I'm also going to half our second solution, pi minus sine to the -1/3 over 2. I'm also going to do the same for the other two solutions. So minus pi over 6 divided by 2 is minus pi over 12. And 7 pi over 6 divided by 2 is 7 pi over 12. And what you have to do now is just double check that they are within the given interval. So our interval for this question is minus pi to pi. So we only want solutions within that interval. And if you double check these on your calculator for the first two here, and hopefully you can see there that these are all within our range of accepted values. Now, of course, there are infinitely many solutions outside of this interval, but because we only want them between minus pi and pi, these are the only ones that we will give for the final solutions. If you wanted to find other solutions that are not within the given interval, all you have to do is add 2 theta or minus 2 theta, multiples of 2 theta, and then you will have more solutions. So let's move on to the second example. We want to find all the solutions to the equation 2 tan x minus sine x equal 0. So firstly, recall that tan x equals sine x over cos x. So we can rewrite this initial equation as, well, let me write here, substitute tan x equals sine x over cos x into our original equation there. And we get 2 sine x over cos x minus sine x equal to 0. So from here, we can multiply through by cos x. So multiply through by cos x. And so you get 2 sine x minus sine x cos x equals 0. Hopefully you can see here that you can factorize and take out the sine x, and so you're left with 2 minus cos x in brackets equal to 0. And now it's easy to obtain our solutions because we can write sine x equals 0. Of course, either sine x has to be 0 or minus 2 minus cos x has to equal 0. So we have to look at both. So sine x equals 0 or cos x equals 2. Now, if we think about this solution here, well, we know the maximum value for cos is 1. So in fact, this has no solutions because there are no values of x for which cos x equals 2. So then all we really care about is our sine x equals 0. So if we were to sketch our graph for sine x, as I've done here, we want all the solutions of x for sine x equal to 0. So we're going to look at the x-axis, where our sine graph intersects the x-axis, and we can see it's at 0 radians, pi, 2 pi, 3 pi, go backwards, minus pi, minus 2 pi, and so on. And there are infinitely many values of x for which sine x is 0. And if you notice, we can generalize this by saying that x equals inverse of sine of 0 if x is 0, pi, 2 pi. It's actually the same for the negatives going backwards. Well, then x can be any integer value of pi. And that will give us sine x equal to 0. And I'll write here for n, any integer value there. Okay, so that's the general solution to sine x equals 0. In the next video, we're going to look a bit at transforming trig functions. So we're going to revisit our compound angles and see how our trig functions shift as we change the variables.